Good afternoon and welcome to our Speaker Series event. My name is Vakhtang Putkaradze and I am Vice President, Transformation, Science and Technology for ATCO, and I will be your moderator today. I would like to start by introducing Siegfried Kiefer, President and CEO of Canadian Utilities Limited, who has some welcoming remarks and will introduce our speaker. Siegfried, in his leadership position at Canadian Utilities, has long played a leading role in advocating environmental concerns of global importance, most notably the promotion of green energy involving hydrogen and electric, both in utilities and automotive industry. The topic of this lecture is therefore of particular importance to Siegfried's interest and as well as ATCO goals. Siegfried, thank you so much for joining us today, and I'll turn things over to you.
Well, thank you, Vakhtang, for that introduction. And I'm very pleased to be able to welcome all of you that can join us today at our first ATCO Speaker Series event of 2021. I'd like to begin by acknowledging the traditional owners of the land on which we are gathered on, wherever you may be located. I would also like to pay my respects to elders, past and present, in the communities and regions where we operate. We have a number of my ATCO colleagues on the call, as well as others from academia, the community, and business sectors. Unfortunately, Nancy Southern, our chair, could not join us today, and I know she had wanted to take part, so on her behalf, we welcome all of you this afternoon. I truly commend our transformation team, led by George Constantinescu, for convening this session and the other Speaker Series sessions that will follow later this year. These sessions are a chance for us to share and discuss knowledge and insights from thought leaders. Our aim is to provide ATCO's people and our network of peers and partners and friends with information on promising developments, trends, and leadership in relevant fields. Our team says this new series will be a mix of both technical and somewhat broader topics. And I think it's very exciting that on February 18th, we'll be hearing about How to Be the Best on Average by Professor Charles During from the University of Michigan. I'm thrilled that in today's session, we'll discuss how the effects of climate change are being studied in Biosphere 2 and the learnings about nature's response to future climate conditions. I'm sure many of us recall the history of attempts at Biosphere 2 to build isolated communities, so it will be fascinating to learn about the current work being done in this facility. We have much work to do in terms of addressing climate change and understanding the landscape evolution under such conditions. With energy transformation in mind, ATCO started investing in alternative and renewable energy solutions more than 30 years ago. In Australia, our Clean Energy Innovation Hub is a leading research and development facility that is a testing bed for hybrid energy solutions. The hub generates green hydrogen through solar-powered electrolysis and is a significant step in Western Australia's move towards a hydrogen economy. Our fabulous Australia team is also performing a feasibility study of a commercial-scale hydrogen production plant. If it goes ahead, it would establish that country's first commercialized green hydrogen energy ecosystem, including a 10 megawatt electrolyzer and a plant capable of producing up to 4.6 tons of hydrogen per day, powering vehicles and industrial applications. In addition to hydrogen, we have extensively studied renewable natural gas, solar, hydro, wind, and geothermal technologies. Some of our successful projects in this arena include the EQUIS Net Zero initiative here in Alberta, where we've also commissioned Canada's largest off-grid solar and storage facility at Fort Chipewyan. That will help that community reduce its diesel use by over 800,000 litres a year. And we are now exploring additional options for incorporating natural gas and generating renewable natural gas from wood waste, which emits up to 85% fewer GHG emissions. I'm very proud to say that ATCO has approached these energy solutions to global problems scientifically and has strived to make these hybrid energy solutions economically viable as well. While we are transitioning to lower emissions, understanding the evolution of the biosphere and the climate around us is also of great value to ATCO. So that gives you an insight into why ATCO is very interested in hearing more about the research and learnings that Dr. Peter Troch will share with us today. And it's my pleasure to now welcome and introduce our guest speaker. Dr. Peter Troch is a professor of hydrology and atmospheric sciences, the Agnes Nelms Houry Endowed Chair in Environment, Joint Professor of Civil Engineering and Engineering Mechanics at the University of Arizona since 2005. Prior to that, he was a professor at Netherlands' largest agricultural institution, and he's now science director for Biosphere 2. His expertise lies in hill slope and catchment hydrology, remote sensing and data assimilation, hydrological predictions in ungauged basins through advanced measurement, modeling and synthesis methods. Dr. Troch, thank you so very much for joining us and expanding our thinking and understanding of these issues. With that, I'll turn it back over to Vakhtang to explain the format of today's session. Vakhtang?
Thank you, Siegfried, for a great introduction to the speaker and this lecture. Again, welcome to all who have joined us. This lecture is the second lecture in the ATCO Speaker Series. As Siegfried has mentioned, the goal of the series is to provide ATCO's workforce and other listeners with the information on the promising development in the relevant fields, outline where the state of the art is now and who the leading experts in the fields are, and what is possible to achieve within 10 to 15 years horizon. The next lecture, also as Siegfried has mentioned, is going to be on February 18, at the same time as today's. Joining us will be Professor Charles Doring, Director of Center of Study of Complex System at University of Michigan. Before we get underway with today's lecture, I would also like to remind you that the session is a one-way video and audio format. You can see and hear the presenters, but they can't hear you. Not the great for audience feedback. That's why we're encouraging you to ask questions. You can do so by using the questions icon at the right of your screen. We will open up question functionality roughly midway through Dr. Troch's lecture. You can address your questions to him. With that, I would like to pass the microphone to Dr. Troch. Great to have you with us. Please go ahead.
Professor Troch, could you share your slides, please?
Yes. Okay, I trust that you can see my screen and the title page of my presentation. And I want to thank both Vakhtang and Siegfried for this wonderful introduction. As was mentioned, my talk will mainly focus on the research that's being done at Biosphere 2 regarding how landscapes will respond to climate change. So the general title is listed in the flyer that was distributed among all of you, and a more specific title of my presentation today focuses on this instrument that we built within Biosphere 2 called the Landscape Evolution Observatory, which is a large-scale controllable infrastructure to study coupled Earth surface processes in the context of climate change. For those of you who are not familiar with what Biosphere 2 is, let me give you a little bit of background. Biosphere 2 is located north of Tucson and southeast of Phoenix, so it's about an hour drive from both airports. And it's one of the major tourist attractions in this area. Before the COVID-19 crisis, Biosphere 2 received about 100,000 visitors each year that tour the facility, learn about the history of the facility, and also learn about the current research that's being done. So in that sense, it's a unique infrastructure where research is being performed in front of the audience, basically, and with active interactions between the researchers and the public. So Biosphere 2 is a unique large-scale experimental instrument or apparatus, which is now operated and owned by the University of Arizona and houses 7 different model ecosystems. It's run by a team of multidisciplinary scientists, and we have a broad science education and public outreach program. And we also have a modern conference center where workshops and conferences can be organized. This is how Biosphere 2 looks today. Today or yesterday, we had a major snowstorm moving into the area, and we are now enjoying a beautiful winter wonderland here in the Southwest desert. This is how it looks under normal conditions. As you can see, it sits within the Sonoran Desert, north of the Catalina Mountains. And it's a 3.14 acre large greenhouse, basically, that hosts several model ecosystems. This pyramid-like structure hosts the tropical rainforest. Biosphere 2 was constructed in the early 90s, so we're talking about a 30-year-old tropical rainforest that is sitting inside the greenhouse. And of the original 253 species, only 80 species have survived the transition, and basically the composition of the ecosystem has adapted to the conditions that are present within the Biosphere 2. The rainforest, the tropical rainforest, is basically how the tropical rainforest will look like in the future with global warming. This rainforest has experienced consistently higher temperatures than what are currently being measured in rainforests such as the Amazon, and therefore it's a golden opportunity for ecosystem ecologists to study how these rainforests may adapt or change under climate change. This long structure is the host of both the ocean, which is a large tank that allows for large-scale experimentation in ocean-like ecosystems, and it's also the home of the upper and lower savanna. Currently, the ocean is being transformed as a research instrument to study the coral reef behavior under rising acidity levels of the ocean and higher temperatures. As we all know, the world's coral reefs are currently under threat and are expected to disappear within the next few decades. So therefore, research in order to try to save those coral reefs under these changing conditions is urgently needed, and this research is led by one of our scientists. That smaller pyramid in the background hosts a fog desert and is currently not actively used as a research model ecosystem, but it's the host of several research and science displays. This structure here in the front represents the human habitat. That's basically where the early biospherians were housed, where they prepared food and ate dinner, and also is the location where many of the labs are situated in terms of both gas and water research. And then finally, those three bays at the background are referred to as the agriculture bays. It's basically the area where the early biosphereans were growing crops to sustain themselves. These agriculture bays are now shown here in this picture. As you can see, there are three bays separated and are of such a scale that within that greenhouse, a lot of research can take place at scales that is unprecedented in other facilities. So these agriculture bays were transformed by the University of Arizona into the now Landscape Evolution Observatory, or short, LEO. LEO consists of three identical hill slopes or landscapes, shown here in this artistic rendering of LEO. And these three landscapes represents hill slopes that are 30-meter long, 11-meter wide, and are 1 meter deep in terms of a soil. The soil that was deposited on these landscapes is a crushed tephratic basalt, basically a physically weathered lava flow, and that will undergo rapid chemical weathering when water is added to these soils. Each hill slope also has a tractile system that can move two people over the hill slopes without having contact with the soil, so that we do not disturb the natural evolution of these landscapes. These transport systems are important for us to be able to reach instruments that need maintenance, or to make measurements from the soil or from the vegetation that will grow on these hill slopes. So what's the reason why we constructed the Landscape Evolution Observatory? One of the things that are poorly understood in earth sciences is how soils, biota, co-evolve and produce resource cycles that are beneficial to life on Earth. And understanding those processes involved is important to be able to make predictions about future changes when the conditions are changing in a globing planet, warming planet. So let me step you through the thought process that we went through to develop this Landscape Evolution Observatory. So initially, when the slopes are just constructed, basically have a very simple system where we know the slope of the landscape, we know the soil depth, we know the geomorphology or the topographic convergence, and we know the hydraulic properties of the soil. With that, hydrologists can make predictions about how water moves through these landscapes. But when we add water to these basaltic soils, the first thing that will happen is that the primary minerals that make up the soil, they will be chemically transformed into secondary minerals that are initially are in solution. When supersaturation occurs in the soil water, these secondary minerals can be deposited, and the chemical weathering of the basalt minerals can also release nutrients that are essential for life to grow. Some bacteria take their energy from iron or manganese, and those elements being released from the basaltic soil are the first energy sources that allow colonization of microbes. Those early microbial communities are autotrophic. That means they can feed basically on elements like light or nitrogen from the atmosphere, or, as I said, iron minerals released by the soil. When that early colonization moves further in time, we expect more heterotrophic microbial communities to be able to colonize the soils or landscapes as well, because they can now feed on the carbon that's been sequestered by the early colonizers. So this early transformation of the landscape creates niches for more complex ecosystems to be able to grow on these landscapes. So the chemical weathering initially was purely based on reactions between water, carbon dioxide, and the primary minerals of the soil. But as we add more complex life forms like vascular plants onto the hill slope, we will see enhanced biogeochemical weathering. And ultimately, we will see whole ecosystem dynamics that are basically reassembling their composition in such a way that they optimally can benefit from the resources available. That will basically lead to a significant transformation or change in the subsurface structure of the soil in terms of its porosity, in terms of its hydraulic properties. Roots will leave micropores or create preferential flow paths through the subsurface. And we will basically transform this early simple hill slope system into a much more complex system that represents what we will find in nature. Now, what we can observe in nature is basically has already undergone this entire cycle several times. And the opportunity that the Landscape Evolution Observatory creates is to study these interacting processes right from time zero. And therefore revealing the feedback mechanisms that take place in these evolving landscapes. So the instrument was developed such that many researchers in the earth sciences can ask many research questions. So there is no single unique research question that led to the design of the instrument. The instrument was designed such that we can ask many questions. Simple questions like, can we close the water, carbon, and energy budget? Surprisingly, in nature, it is very difficult to do that because of the lack of measurements. What's the role of plants and microbes in the geochemical weathering pathways and fluxes? Can we predict the hill slope evolution in a changing climate? How does water balance variability influence ecological community assembly? What is the role of establishment versus competition? So these are sample research questions taken from different disciplines, from hydrology, geochemistry, ecology. And so the team of scientists working at Biosphere 2 represents all these disciplines and create an environment that leads to discovery because of the collaboration of specialists within each field. So having discussed some of the background that led to the design of LEO, I want to discuss with you what LEO really is. So this is a map showing the different sensors and samplers that are embedded within the LEO soil. As you can see, at 5 different levels, from 5 centimeters to 85 centimeters, we have installed many different sensors. In total, there are 1,800 sensors for each hill slope. And those sensors are selected so that we can measure state variables that are critical to study the processes that leads to the coevolution of the landscape. We have soil moisture probes and soil temperature probes at each level. In total, 496 sensors that are sampling the moisture content of the soil as well as its temperature. And co-located with those sensors, we have tension lysimeters, basically instruments that allow us to sample soil water under unsaturated conditions, and the sampled water can then be analyzed chemically for its composition in terms of the primary minerals that we expect to develop during chemical weathering. We measure also the soil heat flux into the slope so that we can close the energy balance of the slope. And we measure at several locations the CO2 concentrations of the soil air. And the CO2 concentration of the soil air is an important indicator of chemical weathering, or possibility of chemical weathering. As CO2 dissolves in water, it creates carbonic acid that is the initial step of the chemical weathering that leads to the transformation of those minerals. We can also sample the soil air and analyze it separately for its composition, as well as we measure the saturated water table that develops during some rainfall events. And ultimately, we have electric resistivity tomography electrodes positioned that allows us to apply geophysical methods to look at subsurface structural change during the coevolution of the landscapes. We also have instruments above each landscape. From the space frame, we have 5 masts hanging towards just above, but not touching the surface. And at 5 levels along these vertical masts, we measure temperature, humidity, wind speed, direction, and photosynthetic active radiation, or otherwise called visible light. Those sensors allow us to basically study the atmosphere above each landscape. We also can take air samples and analyze them in our spectrometers that I will introduce in a minute. You can also see in the background the tractile system that allows us to move up and down the slope. Now, as you can see, we can only move that tractile system up if we remove those masts, and therefore those masts are constructed such that we can pull them up into the space frame and out of the way of the transport system. We also have to do that when we rain on the slope, as rain will be caught by the mass and would lead to unacceptable drip erosion under the mass. We were able to install a remote sensing capability above each landscape. We use infrared imaging to study processes such as bare soil evaporation, how much water is evaporated from the land surface during and after rain events. And we also have hyperspectral cameras that allow us to study photosynthetic activities of vascular plants once they are growing on top of the landscapes. Those cameras are attached to a rail system that you see on the right that is positioned above each and parallel to each hill slope. And we can move a housing or a box that houses those cameras up and down the slope so that we can reach and image each part of the land surface. We can rain on the landscapes with a sprinkler system that was designed to apply rain rates between 4 and 48 millimeters per hour. And to the right, you see the spatial distribution of the rainfall. As you can see, it's not homogeneous as would be ideal, but with sprinkler systems, that's hard to achieve. So we had to map the spatial distribution of each hill slope and irrigation system so that we can correct for any anomalies in the amount of rainfall that certain locations within a hill slope receive. And we do that with some frequency, like annually, in order to see how much that has changed over the year. At the outlet of each hill slope, water is allowed to move freely out of the subsurface and into instruments that allow us to measure the flow rate. As the picture shows, we have tipping bucket rain gauges or gauges that measure the volume rate at which water seeps out of each section of the seepage phase. And they're also connected to an electromagnetic flow meter that measures the rate in a different way and for a different range, so that a combination of both instruments gives us a good measurement of the total flow rate out of the hill slope. So when we know the rainfall in and the outflow out, then we can look at the storage change within each hill slope. So how much water is still stored in the hill slope at any given time of observation. The way we measure storage change is by, we have put each hill slope on top of 10 load cells that measure the relative mass change of the hill slope as it undergoes rainfall input or evaporation output. The graph to the right shows the start of a rain event at constant intensity, which is represented by the slope of this straight line, which represents the increase of the total mass in kilograms. So that's a unique opportunity to measure directly the change in storage of water in a landscape, something that cannot be done in nature. We can compare that with our soil moisture measurements. To the left, you see a picture of one of those soil moisture probes. And since we have 496 of those probes, we can also reconstruct the mass change based on the measurements of soil moisture. And that's illustrated to the right figure. And as you can see, it's not a perfect straight line as the load cells indicated, which means that some of the sensors have a uncertainty in their estimates that we can then correct by using both observations at the same time. As I mentioned, we have suction lysimeters that allow us to sample soil water and analyze it chemically. Initially, we had to pull water using these syringes manually, which required an army of undergrads. And since that was basically not practical, we constructed a vacuum chamber connected to a vacuum pump that is now pulling automatically the specific vacuum that is compatible with the water potential within the soil. So water is held at a certain negative pressure against gravity in the porous material, and when we apply a vacuum that is at that negative pressure, we will release that water from the pore space. And so since we measure the water potential, we can also set the vacuum at the level that samples accurately at the predefined pressure or vacuum. As I mentioned, we have been able to add several spectrometers to our arsenal of instruments. This is a laser spectrometer from Los Gatos Research that allow the analysis of liquid water stable isotopes of deuterium and oxygen 18. This instrument is used to look at the isotopic composition of the seepage water that flows out of the hill slope at the bottom of the slope. And that isotopic composition can be then compared to the isotope composition of the rainwater that we used. The rainwater or the irrigation water comes from 5 tanks that are stored in the basement of Biosphere 2. And with these tanks, we can easily change the isotope composition by adding deuterium or O18. And so giving a specific chemical signature or signal to the input, we can then study how water moves through the hill slope and changes the composition of the output. We can also do that in the gas phase or water vapor phase. and this instrument is connected to our soil air samplers, so that we can also observe not only isotopes of water or hydrogen and oxygen, but also isotopes of carbon in carbon dioxide. Okay, so that's basically what the instrument allows us to do. And now I want to show you a couple of early results, starting with the hydrological response, and then I'll show you some examples of the geochemical transformations that we already have observed. So what this video will show is the soil moisture response of the hill slope to the left when we rain at a constant rain rate of 12 millimeters per hour for almost an entire day. So to the right top, we will see the rainfall pulse in blue, and the red line indicates the outflow or seepage flow. And then the lower right graph shows the increase in mass during this constant rain event, both observed by the load cells and by the soil moisture probes. As you can see, they are different, meaning that we have to correct the soil moisture probes to match better the load cells, which have a much better accuracy. And the load cell, the reason why we know the accuracy of the load cells is much better is because it matches the mass that we add when we rain on the slope. Okay, so what you'll see to the left-hand side are different wetting periods or phases that basically you see the water front or the infiltrating front moving down, reaching the bottom of the hill slope and causing an upward movement of the water table. That leads to the increased seepage flow that we see to the right. These are simple observations in terms of we just look at how the soil wets up during a rain event and how that is different from different places along the hill slope. But realize that these measurements, these simulations are the very first at the scale of a hill slope. So observations made in natural systems do not have the spatial nor temporal resolution that we can reach at LEO. Most of our research is funded through grants from the National Science Foundation here in the United States. And this is an example of a grant that we use to study the coupled hydrological and geochemical processes at the Landscape Evolution Observatory. So we're directly looking at the interaction between water and chemical weathering. These are early results from that research that show the response of soil moisture during a wetting period, during an irrigation period. Let's focus on the blue dotted line, which shows the volumetric water content at 5 centimeters below the surface of LEO. And when we rain at around 11 o'clock that day, we see that the soil moisture quickly rises to a much higher level of about 25%. So that's in the direct response to the rainfall input. The probes at deeper depths, like 20 centimeters and 35 centimeters, they respond later as expected, as the infiltration front has to move into the soil, but they also respond with lower moisture content after the initial increase, which is an indication of the different hydraulic properties at different levels within the slope. Interestingly, we see an opposite response of the CO2 concentration in the soil. So at 5 centimeters initially, the CO2 levels in the soil air were about 300 ppm. And then as we start raining, this concentration drops abruptly quickly to about 100 ppm, which is a 70% reduction. This CO2 being removed from the subsurface indicates that it's actively being a part of the chemical weathering reactions of the primary minerals of the basalt soil. And we see similar response, but delayed at deeper depths. So this is a first observation of direct effects of chemical weathering on the composition of the soil air in terms of CO2 levels. When we match that to the entire carbon mass balance over the entire hill slope, we can confirm that these observations are quite accurate. So the triangles, they represent the total inorganic carbon measured with our CO2 probes, the Vaisala CO2 probes. And these are an integrated estimate of the total inorganic carbon in kilograms. The vertical bars represent the uncertainty. We couple that with a simple carbon mass balance where we compute the total inorganic carbon by accounting for the initial inorganic carbon that we know was present in the soil. We add to that the inorganic carbon that moves into the soil with the atmosphere, so basically with the rainfall. And then we subtract from that the carbon that's being exported mainly as bicarbonates at the seepage phase. And as you can see, the triangles are very close to the solid lines that are a result of calculations based on the mass balance. So one of the questions that I illustrated earlier was, can we close the carbon balance? Well, this illustrates that with LEO instruments, we can actually do that. This type of analysis at the landscape scale in nature would be quite impossible. Now, why is this all important? Why do we collect all this information? Well, one of the most important instruments that scientists have available to predict what's going to happen under climate change is mathematical or numerical models. And one class of these numerical models are referred to as reactive transport models. Reactive transport models basically combine a description of how water moves through the landscape with the geochemical theory that predicts the transformation of minerals as water moves along through the landscape. And the Department of Energy here at the United States is developing these reactive transport modeling to study issues like groundwater contamination, nuclear waste storage, geological carbon sequestration, soil development, etc. And how all this may change as the temperatures warm up. So in order to make these predictions, we need to synthesize our knowledge about these Earth system processes into these numerical models and then run them under different boundary conditions that would be our best estimate of what will happen to our planet, similarly to how we use global climate models to predict evolution of our climate. So the data that has been generated by LEO provides for the first time detailed information about these coupled processes that can improve these reactive transport models that have been around for several decades now, but have been never really thoroughly tested with the detail that provides the data from LEO. There are several well-documented codes available to the research community. Most of them listed here to the left are developed by the scientists of the Department of Energy. And there's an interesting paper about 5 years ago that describes the differences between all these codes. We are using one of those codes to see how we can reconstruct the measurements that we make at LEO. The code is called pFlowTran. And vice versa, we can also use the data from LEO to improve the parameterizations within this code. But we provide freely available data to all scientists that are working with these reactive transport models if they are interested in using the data for model validation. So here's an example of an experiment that we ran a couple of years ago at LEO. What you see here in blue are the rainfall pulses that we applied in a semi-periodic fashion, and the observed response at the outlet of the hill slopes. This is just one hill slope, just to give an example. The red dots give us the modeled outflow. So this gives us a way to validate the accuracy of how the model represents the water flow through the hill slopes. We had some issues during the experiment with some of our observations between day 4 and day 10. And you can also see that we had some more erratic rainfall at those periods. And so therefore, our comparison between model and observations are off here because we do not really trust the observations in this particular situation because we had these issues. But later on during this experiment, we did a pretty good job in capturing the main dynamics of the hydrology. During different cycles labeled A, B, and C, we did collect the samples to measure the chemistry of both outflow and pore water. And with those data in hand, we could run our reactive transport models to see how we can reproduce the observed concentrations of certain elements that are listed here to the right, going from aluminum to silica. And as you can see, there is a reasonable comparison between what we've measured and what we've modeled. But there's also systematic differences, for instance, for manganese, which now allows us the opportunity to study why there are these differences and what needs to be corrected if we trust our observations more than our model. We can also calculate the precipitation rate, so how quickly will secondary minerals form in the subsurface of the Landscape Evolution Observatory. And as you can see, those precipitation rates, they fluctuate with the fluctuating moisture content or storage within the hill slope. And some elements will form very quickly, relatively speaking, in geochemical terms, and some will form more slowly. But all these elements that are listed here are secondary minerals that we know are in solution and are potentially precipitating and therefore changing the subsurface structure and therefore the hydraulic properties of the subsurface. To give you a spatial pattern of a part of the Leo Hill slope, we are looking now at volume fractions of precipitated secondary minerals at 34 days into the experiment, and the different color code gives you the change in volumetric fraction for a specific set or class of species, chemical species, such as aluminosilicates and aluminum hydroxides to the upper left and manganese oxides to the lower right. As you can see, there is a clear spatial pattern in the amount of secondary minerals that are being deposited within the subsurface, and it's different for each species. Now, these different rates of precipitation at different locations within the hill slope will now also lead to changes of some hydraulic properties, such as the porosity, which was initially 42% of the soil, or the hydraulic conductivity, which is a measure of how easily water moves through the slope. And initially that was at 2.37 meters per hour. And because of those chemical transformations in the subsurface, these hydraulic properties are also changing, possibly changing the flow paths of water and therefore changing the complexity of understanding the hydrology of these early landscapes. So we are now building a coupled model called terrestrial integrated modeling system, which combines the hydrology with the geochemistry and ultimately with the ecology, such that this integrated model will allow us to make predictions about landscape changes in a changing environment. Such a model does not exist at this moment, but with the data that we are collecting at LEO, we are confident that we will be successful in coupling those individual components of Earth system models and provide that to the research community so that we can improve our understanding of the effects of climate change on our environment. So in conclusions, I hope I could convey that the Landscape Evolution Observatory and in more general ways, the entire Biosphere 2 offers unique collaborative research opportunities for Earth scientists. I briefly mentioned the research that we can do in the tropical rainforest, the research that we can do in the ocean, and then a more detailed research done at the Landscape Evolution Observatory. The unique feature of our research is that we have interactive cycles of large-scale experimentation and numerical modeling. So we collect data at the large scale during experiments, and then we compare our observations with numerical models, and then either improve our numerical models or double check our observations. So through these interactive cycles, we can make rapid progress in our understanding of very complex coupled Earth surface processes. The amount of data that we generate each day is available to make improved parameterizations that are critical to accurate Earth systems modeling. And these are the tools we will rely on to understand how our environment will change during climate warming, but also, and maybe more importantly, how we can mitigate some of the negative effects that we foresee. So with that, I thank all of you for your attention, and I think I'll give the mic back to Vakhtang.
Thank you, Professor Troch, for this wonderful lecture. And we are ready to dive into our Q&A session. A reminder to use the question icon to ask questions. It's moderated format, so once the questions are published, you can see them and upvote if you like. I will do my best to select a broad range of questions. So I wanted to start with a comment from Lillian Brewster, who is our Vice President for Indigenous Stewardship. It's not a question, she says. And Lillian says, thank you. This is more of a comment. This is so relevant to the climate changing and more specifically above the Arctic Circle and how that will change the soil and water levels, which affect the soil. I don't know if Professor Troch wants to comment on that as well.
So to make sure that I understand the question, the question is about how this research can also help improve our understanding of Arctic environments?
Yes, that's correct.
Okay, so that's an interesting question. So of course our system is limited in terms of the type of climate that we can impose to our landscapes. As the Biosphere 2 is located in the Southwest US desert, it's a northern desert, most of the time we are experiencing warm weather, warm climate. So our research is most relevant to places that have basaltic landscapes, so that basically are similar to the landscapes we have within Biosphere 2, and that have experienced a climate that is sufficiently warm and sufficiently wet to allow the chemical weathering rates that we are observing at LEO. Having said that, one of my colleagues in hydrology, Professor Jeffrey McDonnell at the University of Saskatchewan, he recently built his own LEO, and he has the capability of create frozen soil conditions. So complementary to our research, the research of Jeff is very relevant for the question that was asked.
Thank you. So next question is, how long in years are you anticipating to monitor the impact of climate change in the biosphere too?
Good question, and an aspect that I did not address. The initial idea was to run the experiment for 10 years with basically 2 phases. The first phase, the bare soil phase, which we are currently concluding. And the focus during that phase was on the hydrology, the geochemistry, and the microbiology. I didn't show any examples of the microbial research that we've done, but we are basically actively looking at the interaction between water, rock, and microbes, and how microbes facilitate the chemical weathering, and how they help in creating soil aggregates that improve the structure of the subsurface. The second phase is what we call the vegetated phase, or vascular plant phase, where we basically introduce seeds from annuals, which is currently the idea, and study different generations of annuals and look at ecological questions such as genetic type. How does it help in terms of colonizing certain parts of the hill slope? So it was expected that we could conclude or complete that work in 10 years, but as we started experimenting with LEO since 2016, and we are still in the bare soil phase, I anticipate that our research will basically go on for another at least 10 years.
That is great to hear. Thank you. That we have 10 years more of great science coming out of your group. The next question I wanted to ask is from Mike Whitall, and he asks, you noted that the rainforest has experienced a reduction in number of species and related it to the greater temperatures that the species would naturally experience. Were other factors, including soil nutrients, fungi, naturally occurring insects, etc., that all contribute to plant health, consistent with natural occurrence? I'm interested to know if heat is the only reason or if other reasons also had influence. Thank you.
Mm-hmm. Yeah, that's an excellent question. I would say short answer is no. The tropical rainforest growing within Biosphere 2 is a model system, so it's not an exact replica of any rainforest such as the Amazon, but it has sufficient features that allows us to draw some conclusions about possible responses of these complex ecosystems. One of the work that we currently are doing at the rainforest is to study the importance of isoprene emissions by plants, by trees, in order to regulate their temperature and improve their photosynthetic efficiency. It was discovered that isoprene emission is an important mechanism used by plants to regulate leaf temperatures. And some species in the Biosphere 2 are isoprene emitters and other species are not. And the question we are trying to address is how are non-isoprene emitters adapted to the Biosphere 2 climate that allows them to be successful, compared to the isoprene emitters that have a natural defense mechanisms. Those are some of the above ground observations we can easily make. Below ground, but as was mentioned, nutrients, fungi, all that is something that still is left for further research.
Thank you. Next question is there an application of this research in space exploration, such as creating biological environments supporting colonization of the moon Mars? And that's from Anonymous.
Mm-hmm. Yes, there is. As we know, most of the Mars surface is a basaltic rock, very similar in its chemistry to the material that we use for LEO. And so the knowledge that we will gain in the early transformation of basalt rock into a life-sustaining ecosystem will have applications in whenever we want to do terraformation on other planets, especially if there is basalt rock as a substrate. So, of course, we probably are still far away from the practical applications, but it's definitely a very active field of research that we are pursuing at Biosphere 2.
Thank you. And I guess you theoretically could change the atmosphere composition to fit whatever Mars atmosphere is. You know, pressure is probably a little bit difficult, but the composition is possible.
The chemical composition, theoretically, we would be able to do that, as we can run Biosphere 2 as an isolated system from the environment.
Yeah, thank you. So on that note, a relevant question also from Anonymous. Since this is a closed system, are the microbes chosen and introduced, or do you rely on existing microbes from the local area?
Initially, the Biosphere 2 was planned to be used as a closed system, so completely isolated from the environment. As the UVA took over, we decided to run it open. So that means that we have free movement of air and its constituents through some openings in the structure. Reason for that is that it reduces our energy bill significantly during summer. But of course, that also results in some loss of control in what you basically would allow the landscapes to be exposed to. Now, microbes are everywhere and ubiquitous, and the scale of our instrument is such that any experiment with a certain species of certain microbes would be futile, as it's impossible to keep it sterile initially. So we allow for natural contact and colonization of microbes that are around, and us scientists that move into the space on a daily basis, we carry with us those same microbes and expose them to the LEO surfaces. So we've chosen to observe rather than control that aspects of the landscape evolution.
Thank you. So the next question is also from Anonymous, and there are actually 3 sub-questions. Does Project Eden in England do similar research? First one. Second, what are the top 3 learnings you have acquired so far? So maybe you can summarize that. And third one is, what is your research telling us about crop growth and / sustainability, and also energy sources and needs of crop growth?
Yeah, excellent questions, and let's see if I can recall them all as I try to work my way through them. So I already forgot the first sub-question.
Project Eden in England.
Oh, project in England?
Eden in England.
Okay, yeah. I am aware of Eden. I don't know much detail of it. It's a similar facility with greenhouse ecosystems, but the focus of the research is quite different from what we do at Biosphere 2. And it also has a much stronger tourist component, if I am not mistaken. So yes, there are similarities, but there are also significant differences. And the main difference is our focus on landscape evolution, which is not done at Eden. The second question was on the three main take-home messages that we've learned so far. First one, I would say, it's damn hard to run a large-scale experimental facility. I always refer to LEO as an instrument, a scientific instrument that sits between the laboratory scale, where we can have high control of our experiment, but we suffer from the small scale of our observations, and then the real world, where we have no control of what's happening, and but we are studying a real system at this appropriate scale. And LEO sits in between. It's much larger than a laboratory experiment. It's much more controlled than what's happening in nature. But because of its scale, it's not completely controllable. So that's the first lesson that I've learned in terms of expectations prior to working at LEO. I think in terms of geochemical weathering, there is a lot of debate in the literature about using chemical weathering to sequester carbon, and specifically basalt substrates are looked at in order to create surfaces on Earth that would sequester carbon dioxide from the atmosphere when the minerals are weathering. And so there are some geoengineering propositions published in the literature that suggest that that would be a good way of helping reducing CO2 levels in the atmosphere. Our research has shown that that is true, but there are also limitations in the rate at which that will happen because of the strong drawdown of CO2 when the surface gets wet. We also see a strong decrease in chemical weathering rates, and so there's like a Goldilocks situation where you have wet enough basalt, but not too wet so that CO2 gas is not present. And so basically we discovered that there are limitations to what was initially proposed in the literature. I think that's an important addition to our knowledge of geoengineering. Yeah, those are the main issues that I think deserve highlighting. And then the third question.
What is it is telling us about crop growth and sustainability to energy sources and needs?
We have no plans to actually grow crops on, well, that's actually not true. Together with my colleagues in ecology, we are currently debating whether we would use model species similar to alfalfa to be the first vascular plants that would grow on LEO. And we're currently investigating whether alfalfa would be able to grow on the soil. So if we are able to grow alfalfa on the soil, that means alfalfa is one of the major crops in California, and also one of the major water consumers of the water in California. That it will definitely tell us a lot about that particular crop, which is a fodder. It's not a crop used for human consumption, but it's definitely an intermediate product for agriculture. So there I see relevance, but in general, just growing plants in such a poor nutrition environment will definitely inform us about how easy it will be to grow crops on other basalt landscapes other than Earth.
Thank you. The next question is from here. Blessing Okeke, and the question is there any political or government influence to this research? And there was also a similar question that I would like to find, but can't immediately find the actual question. But it said, what did your research do for the local appreciation of climate change in Arizona, locally and globally?
Mm-hmm. Yeah, good questions. We do not have any political pressure or influence on our research. It's basically run by the University of Arizona through many faculty that take an interest in research at Biosphere 2, and that I happen to represent as the science director. But there are many people that are helping me in developing the research agenda. Our funding is basically coming from funding agencies like National Science Foundation, possibly DOE, possibly NASA, mainly NSF though. And those grants are approved by our peers. Our proposals are read by our colleagues, and if the colleagues consider the proposed research of importance for earth sciences, then we stand a chance to get the funding. So there's no instant there is any influence from local governments or politicians in general. In terms of local communities, as I mentioned, we had about 100,000 visitors each year, many of which are K-12 schools that come to Biosphere 2 and enjoy certain educational programs. And those educational programs are always centered around questions of environment, questions of water, questions of energy, and in general questions of climate change. So that's the direct effect we have on our communities. Together with people that have visitors, and they take them to Biosphere 2, and during every tour they are confronted with our research and with specific issues related to living in a desert.
Thank you. Now this, I have a question that is kind of close to my heart, being a mathematician from my profession. What is your methodology, from Anonymous, what is your methodology for determining the accuracy of mathematical models in relation to the observations, should they be in argument of each other?
Mm-hmm. Good question, and a tough one. So mathematical models use equations that may or may not be directly based on physics. An example is some of the transformations that, for instance, if I take a simple example, the way plants transpire water is a biological process. Its mechanics poorly understood. This process is therefore represented in models, hydrological models, by using simple relationships between the transpiration rate that can be measured at some instances and the moisture content within the soil. And we know that's a reasonable assumption that if there's no water in the soil, transpiration will be non-existent. If there's a lot of water, that typically leads to high transpiration rates, but there are other effects on that. So instead of using mechanisms that are of biological physical nature, we use parameterizations. And those parameterizations represent uncertainty right from the get-go. And in reactive transport models, there are a lot of such parameterizations. And so we know that there is a high uncertainty in how we represent certain processes in our models. So we need carefully collected data in order to test how relevant, how accurate those parameterizations are. So it's of course always a balance between the uncertainties from your measurements and the uncertainties from your model, but a careful selection of data and focus on specific subcomponents of models will allow us to improve them.
Thank you. So next question, it had two parts, but one part about how the research project is funded you already addressed. But the second part is COVID-19 affecting the research presently? You mentioned a little bit about the public facing avenue aspects of your of Biosphere 2, but the question is more here about the research.
Yes, when we all went in lockdown in March of last year, for several weeks we were not able to get access to the facility, not until we established a certain protocol of how we could sustain the research at the facility. Since then we've developed a way to deal with trying to minimize contact between scientists and avoid spreading of the virus. So it has directly affected us in terms of having access and how many people can have access at the same time. But in all cases, we have been able to manage, continuing our research.
Mm-hmm. Thank you. So we are just a few minutes away from the end. So I just have a couple more questions, and maybe then we can finish. So the next question is from, I hope I pronounced it correctly, Neil Slingerland. And the question is, great center, thank you for sharing. What landscape evolution models have you used with LEO, i.e. Siberia, Caesar, Lys, flood, other?
Okay, we've got a geomorphologist among us. So the landscape evolution models that this person refers to are models that allow us to study the geomorphological structure of landscapes. As mountain ranges erode or as landscapes erode, those models are able to reconstruct the evolution of the channel networks and the hill slopes of such landscapes. Those landscape evolution models are typically have a somewhat restricted focus in terms of being used in geomorphological research. Now, they become more and more sophisticated in terms of adding more processes related to vegetation or even hydrology. But initially, those landscape evolution models were mainly focused on explaining geomorphological structures that we see around us. So we have not used any because most of the geomorphology that was imposed by how we designed the hill slope is still in place. We have not allowed significant surface erosion, and therefore a need to run these landscape evolution models did not exist yet. But yes, I'm familiar with some of the models that were mentioned, like Siberia. Yeah.
Thank you. So the next question you also partially answered, and it asks, first part is the environment in LEO hermetically sealed, and you already addressed that. But the next question is, you mentioned wind speed measurement. Is it to measure convective movement within LEO?
Good question. So we have simple wind vanes that measure wind direction and wind speed, the propeller types. The reason why we added those is that when we run our air handlers to change the temperature of the atmosphere of LEO, we create turbulent conditions in the atmosphere. Now, the turbulent conditions created by those air handlers is not sufficient to break the inversion that is present in the atmosphere. We have much higher temperature near the space frame than we have near the surface. And normally the temperature is highest at the surface and then decreases with height. In order to break that inversion, we are currently investigating how we can turn each bay into a wind tunnel. So basically creating turbulent conditions in the atmosphere that would be better represent the outdoor conditions. That's why we have those wind direction and wind speed measurements. But we also, and I forgot to mention that, we also have a 3D sonic anemometer, which is an instrument that allows you to measure the turbulent intensity of the wind field in 3 dimensions. And so with that instrument, we can definitely look at convection patterns during the daytime. So, yeah.
Okay, thank you. So I guess 2 more questions quickly, and then I think we'll finish. And first one is, are further studies planned for different soil sources like limestone and basalt, and how transferable are these findings for different soil sources and environments?
Yeah, good question. Well, we will continue the experiment with the basalt because it takes time to, establish a coevolution between soils and biota. As we continue into our experiment, we also see a decline in the amount of sensors that are still working. The sensors were placed in 2012. And so we are currently in the 9th year of using these sensors. And we see that, for instance, soil moisture probes are dropping out. And at some point, we will lose observation capability. But the instrument will still be there. And so at that point, we can decide that, okay, we terminate the experiment as it is, and should we consider different soil type? That's a question for future generations. Maybe I'm no longer involved, but there is definitely an opportunity to do different type of investigation, different soil type or whatever. But the metal structure is there and can be used for future research.
Thank you. And then the last question is why LEO surfaces were built with a slope? And if I may, I can add, if you had built a horizontal LEO experiments, what would you expect to see differently?
Good question, and it's something I should have mentioned. When you're doing research on the flat surface, there is no lateral or minimum lateral interaction between the different processes. Okay, so the scale of LEO wouldn't matter that much if it was a flat surface. Now, having a slope leads to redistribution of water and nutrients and creates heterogeneity within the hill slope that creates different niches for species to be successful. So then what we see in nature is the natural assemblage of species within an ecosystem that compete for available resources like water and light and nutrients. And if you eliminate that heterogeneity, you eliminate that competition. And so in order to be able to address more interesting ecological questions, the slope was essential. And not only is it the slope, but it's also a convergent slope. So basically, we create a place where most of the water and nutrients and end up. And so that heterogeneity is super important to be able to make it more complex, a more complex life form.
Excellent, thank you. Well, I think this is the last question we have time for. Thank you very much, Dr. Troch, for this very interesting and informative lectures. Thank you, the organizers, and thank you, Siegfried, for taking time to join us today. And I hope to see you all on February 18th. And also, I also hope that some of us who are present in this lecture will have a chance to visit Biosphere 2 in person sometime in not so distant future. So thank you, everybody.